Okay, we are recording our session. This is, in fact, week 10 of our 12-week course, so congratulations. We're closing in. We've come a long way, I think, in terms of talking about predictive modeling, and yet I want to finish strong. We've reached the point in the course, and I think I mentioned this a little bit last week, where you'd like to sort of separate yourself from focusing entirely on keystrokes and moving into a broader picture of, okay, what does this really mean? What would I do with the information once I've built the model? And there's not a lot we can do because we don't have specific scenarios. But just as, again, I'm not here just to teach you the software. I'm here to provide you with some, hopefully, material that'll help you when you get out in the real world. And one of the things you're going to have to do, again, is, as we talked about in 610, for those of you that took that course, you've got to turn the results of your model into something operationally implementable. You've got to change something. So when you step back, again, focus a little more on whether there are any insights gained in the models. And of course, one of those key insights would always be, does my model, or the one I chose out of my many models I may have built, does it actually improve on what we're doing without the model? That's the bottom line, isn't it? And then the second insight might be, how hard would this be to implement? Well, we're moving into an area where that second bullet that I mentioned, how hard would this be to implement, is definitely becoming ramping up, because ensemble models, as nice as they are in terms of accuracy, are much harder to implement. You'll see why when we get through a little bit of that. The second point I'd like to make is, of course, we're going to have one more assignment, and one option in that final assignment is to use an ensemble type model. Still have somebody who's not muted. There we go. Is to use an ensemble type model and go through the hoops on that. Now, the ensemble piece to this course is basically added this semester. We dabbled in it very briefly last semester. Remember, last semester was the first time we had been through this course. It was the first time it was offered, and so we went a little bit slower. I was learning as much as the students in some areas, and so we had, and believe it or not, we had more problems with SAS Enterprise Minor then, because we were still getting accustomed to it. So, we've added this, so I think there's a lot more for all of us to learn on ensembles. Certainly, it's probably new for most of you. It's relatively new for me, and I'm learning as I go. And the key thing I would say from SAS Enterprise Minor point of view is again, SARMA, Chapter 7, especially pages 402 to about 411. You don't need to read that whole chapter, but that part is quite good at outlining how SAS handles ensemble models. Since we only have the 1 week on ensembles, I'll try to combine a little bit about what ensembles are with a little bit about how SAS handles them in this lesson. Now, we don't have, as I said, don't have a specific assignment where you have to build an ensemble, but it is an option in your final assignment, as you'll see in the guidance when we get there. But for right now, let's just sort of talk about a little bit about what the heck we're talking about when we say ensemble models. So again, here's my agenda, a little bit of a background, why we even think about this, and then overview a little bit of SAS and how it handles ensembles, okay? Background, well, why would you consider an ensemble? Basically, an ensemble is a combination of models. It's putting multiple models together. So why would you consider that? Well, the bottom line is for one reason: better accuracy. Better accuracy. Oftentimes, not always, it'd be too easy if it were always, but oftentimes the ensemble model will in fact outperform any of the other models, okay? Not always. Depends on the model, and as always, this is sort of like adding something new to the pot. We've talked about decision trees, we've talked about regression, we've talked about neural nets. Now we're going to talk about ensembles, which basically take those things and tweak them or combine them or boost them, a term you'll hear quite often, ensembles. And in many cases, you get a more accurate answer, okay? Now, what the heck are they? Well, there can be combinations of two or more models, okay? You'll see in a moment the little example right out of SARMA where they built 3 models: a regression, a neural network, and a decision tree for one problem. And then they were able to combine those. Now, that's different than just looking at the 3 and seeing which one is the most accurate. We've done that with the comparison node. This is different. This is an ensemble node that lets you basically combine aspects of the models. There's also specialized techniques, okay? And some of you already did that when you were doing your decision tree problem. Some of you went and did the gradient boost. Most didn't, but some did, which is a boosting technique. So there are specific techniques that have become very popular. Bagging, which is sort of an acronym for bootstrap aggregating, boosting, and again, gradient boosting is one such boosting tool, and random forest, which is a decision tree kind of tool. So we can have multiple techniques, okay? Often they deal with decision trees. The advantages, as I said, improved accuracy. They will improve your accuracy. Whether it'll be enough to offset the downside, you'll have to determine as always. And improved robustness. Basically, ensemble models allow you to mitigate the impact of outliers. You know, outliers can have a serious impact on most models because it skews the model to have to sort of account for those. And when you build multiple models with samples of the data, you oftentimes ameliorate that or mitigate the effect of those outliers. So that's very helpful. The drawbacks, well, the biggest one I've already told you. You lose interpretation. If it's hard to interpret a neural network, it is, or even moderately hard to sometimes interpret a regression equation, especially a logistic regression, and it is, relatively easy to interpret decision tree. Guess what? When you have an ensemble which combines models, the interpretation is basically gone. So if you need a model or an approach that simply predicts, you're in good shape with ensembles. If you need an approach that you can use to explain, you're in bad shape with ensembles. And that's an important trade-off, isn't it? It has nothing to do with the efficacy of the modeling. It has to do with how well or easy it is to sell the solution within your organization for a specific problem. If you had an enlightened organization or an organization that was well-versed in the area of analytics and they understood ensembles, we may say we don't really need to worry about how you got there. If the ensemble model gives us the best answer, we're going to go with it. If you had an organization that scratches its head and says, what's an ensemble, and how are you going to tease out what impact, what specific things in the ensemble model actually cause the results, you're going to have problems with that because it is difficult. Just as it's difficult to tease that out of neural nets, less difficult to tease it out of regression, and even less difficult, of course, to tease it out of decision trees. Now, these are all important aspects. We've talked about it over and over again, that what organizations expect a data scientist to do is not just build models and say, here you go. They expect the data scientist to be able to help frame the model, work with the functional area people to understand the data set and the specific problem being addressed. And then they expect the data scientist not only build the model, but be able to explain and articulate something about the model, sell the model, and help operationally implement the model. So we always come back to that, but I think it bears mentioning. It can be computationally expensive to build ensembles. That's a lesser drawback because, again, as you know, with programs like SAS Enterprise Miner, things happen very quickly. We haven't used any Teradata-sized data sets. We'll talk a little bit about that in week 11 and 12. But even with large data sets, I saw a demonstration, and I'll probably give you a link to it. It was a video where they looked at 1 billion records, and it only took a few minutes, okay, to do some analytics on that using SAS Enterprise Miner. And we'll talk about things like the HP nodes and things like that, high-performance nodes, and so forth. Difficult to deploy, yeah. I mean, you get an answer, and somebody says, okay, can I turn that into an easily implementable template or rules or something? And the answer is oftentimes not. We can run through the model and tell you the answer and do something with that, but it's difficult to deploy. So there's trade-offs, as there are with all of the things we've talked about. That's what makes it sporty. If it were black and white, clear-cut, one does this, one does that, then who would pay you big bucks to be a data scientist? Continuing the background, I taught and put together a course on decision making several years ago that we used in the MBA program and the CIO, Chief Information Officer program. One of the things we looked at in our decision making era a portion of the course, was The Wisdom of Crowds. I think it's a great, great book written by James Surowiecki several years ago. The Wisdom of Crowds. He has overwhelming evidence in there based on real-world cases and real-world experiments that under certain controlled conditions, a crowd or a group of people can make decisions outperforming experts, single experts. Think about that. A group of people, relatively informed but not experts in an area, can make a decision as a group that is better than an expert in the area can working individually. So we're not putting groups of experts together. We're putting people together who meet certain criteria that I'll talk about in a minute. But they're not experts, and yet they come up with better answers than the experts. It's kind of amazing, isn't it, to think about it. It ties a little bit into, again, the little sidebar here. As many of you know, machine learning has invaded the world of chess because that's sort of considered the holy grail. So you can really figure out all the moves. Of course, one of them, Big Blue, beat the chess master many years ago in the 1990s. But what they're finding out now is that there are chess masters who are quite good. There are machine algorithms that are quite good. But the winners are usually a combination of people working with the machine learning algorithms. In other words, the algorithm says, move the queen to here, and they say, no, that's not quite right, we're going to move it here. They actually win the competitions more than anything. So it's an interesting combination. So we use the wisdom of crowds as one sort of aspect of decision making in that course, and here it is resurrecting. In fact, in Dean Abbott's book, which is quite good on predictive analytics, he talks about the wisdom of crowds. Okay, the wisdom of crowds dates back to the Condorcet jury theorem. If each voter has a probability P of being correct, and the probability of the majority of voters being correct is M, then P greater than 5 implies M greater than P. Okay, in other words, if each of the jurors has a probability greater than 5 of being correct, then M, the overall majority, will have a probability greater than P. Okay, interesting. Now, going back to the wisdom of crowds, the Surowiecki book, these were the sort of criteria that had to be met for the wisdom of crowds idea to work. First of all, you had to have diversity of opinion. You don't want to have a bunch of people who are identical. Groupthink will set in, and they won't look at a wide variety of possible answers to the problem. Secondly, they have to be independent. Okay, they're not members of a herd where they follow the leader. No, their opinions aren't determined by the opinions of those around them. Third, they have to be decentralized. In other words, they each know something slightly different. They know parts of the problem. They also know some other aspects they can bring to work. And then finally, there has to be a mechanism for aggregating these things into a collective decision. Again, if you go to the links I've got here and look at some other links for wisdom of crowds, you'll see some rather interesting and fascinating things. Okay, so what has all this got to do with ensemble models? Well, we can do the same kind of thing. In fact, in Dean Abbott's book, he talks about, each ensemble model is really a diverse opinion. It's a different answer. Each ensemble model is certainly independent. The models don't look at each other and say, oh, I'm going to do what you did. They're certainly decentralized because they're built by people and they may be in different techniques, and certainly, and then there's a way of aggregating. Of course, right in SAS Enterprise Miner, there are 4 ways of aggregating ensemble models. We'll talk about those briefly. So again, I would recommend Dean Abbott's book that just came out a couple of months ago. It's an excellent book, really easy to read, but quite thorough. Anyway. Okay, so the ensemble approaches that are out there that are very popular, bagging, where you build multiple decision trees, use resample data with replacement. In other words, you build a sample, put the data back in, build another one, and you apply the predictions. This has been applied quite a bit to logistic regression. And I'm hoping, again, we didn't do much with this last semester, but I'm hoping some of you will have enough interest in ensembles that you may take this on in your final assignment and say, I'm going to build an ensemble model of one sort or another. Okay. So bagging, key questions. If you're going to build a lot of models, how many do you build? Well, this is again some guidance right out of Dean's book, the Abbott book, Predictive Analytics Principles and Techniques for the Professional Data Analyst. How many bootstrap models you have? Fewer when the target is numerical. More when the target is categorical. So there's some general guidance. See, remember I talked about I'm trying to put together general guidance for all of our techniques that I can have in a little template, white paper, whatever you want to call it, for future classes. And so I'm looking at what others say are good rules of thumb, and these happen to be some good ones, I think, for a bagging. Again, if it's a categorical target, build more models. If it's a numerical target, fewer models. 10 to 25, the usual number. So there's some guidance. How do I combine them? Well, we're going to talk a little bit about how SAS Enterprise Miner combines them, but these are the common ways: averaging, voting, maximum probability, weighting. And again, each of those has an equivalent aspect in SAS Enterprise Miner. Again, outlined well in Sarman. I've got it in a couple of slides coming up. What if the models are correlated with each other? Interesting. You can have model correlations. Okay, so if the models are very high correlated, in other words, greater than 0.9, then you're not going to improve much because they're almost identical, right? They're almost the same model. Low correlations that indicate that the models are predicting accurately on different records. Remember, you're pulling records, you're sampling them, so each model has a different subset of the data set to work with. So you do need large data sets. You're going to do this, or should have a robust data set. I would think you'd want at least 10,000 or more instances. And so if you get a low correlation, it means the model pulled certain records out that the other models didn't. And that's what you want. You want to account for each of the variations in different ways. So these are some guidance. Boosting, the second approach, instead of bagging, boosting. Build a simple classification model, slightly better than random chance. Each record has equal weight, errors in predicted values noted. Okay, so that's a simple thing we always do, right? Then build a second model. The records that were correctly classified have the weight reduced. The records from the original model that were incorrectly classified have the weights increased. Now, what does that tell you? It says, well, I'm trying to give greater weight to the ones I missed on so that I will try harder to fit to those, right? In other words, I got 5,000 correct, but I got 800 wrong. Well, I'm going to give those 800 greater weight next time I build another model, another classification model. And by giving them greater weight, it forces the model to say, oh, those are much more important than I thought they were. Maybe you duplicate them to give them greater weight. There's other ways to do that. And so the model tries harder, the second model tries harder to fit those in and get those correct. And you continue doing that. Okay? Really a pretty slick idea. You know, it's kind of neat, I think. Well, I'm anxious to see how it works. So how many boosted iterations, again, from Dean Abbott's book, how many boosted iterations done? It says often hundreds of times. Wow. Until the most difficult cases are classified correctly. So if it keeps missing the same cases, you need to, keep tweaking the weights until it finds a way to fit those cases in. How do I combine the bootstrap model results? Weighted average of predictions from all boosted models. That's a different approach, isn't it? Pretty interesting. And what problems are suited for boosting? Well, he says they're designed to work with weak learners, i.e. simple models, and used most often with decision trees. You will find a lot of the boosting techniques, whether it's random forest, add a boost, or even bagging, work quite well with decision trees. Remember, decision trees are probably the easiest models to build, but oftentimes, not always, oftentimes the least accurate. And so the boosting techniques have been applied quite rigorously to the decision tree approach. One of my favorites, random forests. Build one decision tree from each, again, sample, bootstrap sample. At each split in the tree, only consider a random set of inputs, not all. Remember how decision trees work. They consider all inputs, all possible predictor inputs, and all possible values of all possible predictor inputs in order to come up with with each split. So now with using random forests, not only have a sample of the data, you don't have all the data, but you also only look at a random subset of the inputs for consideration. So obviously you're going to get different trees every time you build one, right? A different set of inputs and a different set of records. You're going to get different trees. So clearly the splits will occur at different points for different trees with different inputs. And then you combine this with, again, a majority voting. Final results usually more accurate than bagging, often even more accurate than boosting. Now, last semester, we didn't do, as I said, we didn't do a whole lot with ensembles. We looked at it briefly and then talked about it, and some of the people tried that. We, interestingly enough, if you look at the literature, you see several mentions of the fact that random forest are not included in SAS Enterprise Minor. Well, as we found out this semester, at least one of your fellow students has, credit Lanesh Dave, he checked, and if you use the HP forest node, which is there, you can do random forest. HP is the high performance node, and we'll talk a little bit about what those actually are, sort of specialized things. But you can take a shot at doing random forest. So we'll come back to that. Somebody will try that, I'm sure. There's another form of ensembles that are different. Heterogeneous ensemble says you just build multiple models using multiple methods. In other words, no bagging, no boosting, just multiple models with multiple techniques. Now, we've done that. Some of you have built multiple models for some of the assignments. You may have built a regression model and a decision tree, or a neural network and a regression model, or maybe you built all three, or maybe you thought about that. Okay? Then, so this is a different type of ensemble. First kinds were basically tweaking a certain aspect of the model. This is saying, no, I have multiple models. Both are outlined clearly, I think fairly clearly, in the SARMA book. And so I'm going to say a little bit about what SAS does. Okay, we do know that there's one certain, for sure, boosting technique included in SAS, and that's gradient boosting. Okay. There's also an ensemble node. The ensemble node does something different than the gradient boosting. Okay. The gradient boosting resamples the data set several times and generates results that form a weighted average of the data sets. So it takes a sample, builds a model, takes a sample, builds a model. And it builds decision tree models, which together form predictive model. So it's not unlike random forest, except it's not doing a subset of the inputs. Okay. According to the SAS literature, the gradient boosting often is even better than random forest. In fact, they're quite proud of it, which is why they push the gradient boosting. So you're building multiple trees with resampled data. So you can't use the whole data set, obviously. Now, one tree in the series, the first tree in the a tree in the series is fit to the residual of the prediction from the earlier trees. So we're taking the residual of the prediction from the earlier trees in terms of the derivative of a loss function. Wow, getting complicated. For squared error loss with an interval target, the residual is simply the target value. This is the key. For an interval target, this works pretty well. Simply the target value minus the predicted value. Okay? Target value minus predicted value. So we have a number. And then you grow a tree on that. The successive samples are adjusted to accommodate previously computed inaccuracies because each one is weighted according to classification accuracy, called the stochastic gradient boosting. Okay? You can use it for all kinds, but it works best for interval. So anyway, that's gradient boosting in SAS. It's a node right there. The other way to do ensembles in SAS is really to use the ensemble node. Okay, the ensemble node. Now, the ensemble node does something rather interesting. It creates new models by combining the posterior probabilities, if it's a class target, or the predicted values for interval targets from multiple predecessor models. And then the new model, remember this ensemble model creates a new model, is then used to score new data. You can include bagging and boosting as options. Now, here's one key. The ensemble node, if you're going to put that in your diagram, it has to come in a process flow diagram after a model node, because it doesn't have any, it doesn't go through and build a new regression model or a neural network model or a decision tree model. It builds a model sort of by combining those models, and I'll show you that in a second with what's done in SAS. So when you run a process flow diagram, you have multiple models. Maybe you have a decision tree, a neural network, or regression, or 5 or 6 regressions, or 3 or 4 decision trees, all in your flow diagram, and you connect them to an ensemble node, then only the ensemble model results are assessed. Okay, so the ensemble node sort of takes over and says, okay, I'm going to take all this stuff you've done prior, and I'm going to create a new model which basically aggregates the results of all those previous models. That's kind of the key. Aggregates in certain ways that I'll show you the results of those previous models. You still get assessment charts, lift, profit charts in a model comparison node after that. Okay, so here is the example right out of SARMA Chapter 7. Again, pages 402 to 411. SARMA Chapter 7 is your required reading for the week anyway, so you may already have looked at this. He does a real good job, I think, starting again, page 402 to about 411, of explaining this. He's using a data set where he's trying to predict the probability that someone will attrit, or think of churn. Okay? 1 means they will, 0 means they won't. And he goes through the usual thing. There's a data set, you partition the data set, you impute for missing values, then you build, he built 3 models, a regression model, a decision tree model, a neural network model. That doesn't show all the other things. May have transformed some of the variables and so forth. But anyway, we know all about this. Then you hook up this ensemble node to the end. What does that do? Well, it's going to look at the results of these 3 and say, okay, that's going through. Create some new variables. Okay, let's say the logistic regression model comes up with a prediction of 0.6 probability that the person will attrit for a case, 0.4 probability that they won't attrit. The new variable will be created by the, well, these are all new variables, but again, we'll look at that and say, okay, 0.6 is bigger than 0.4. I'm going to call this, I'm going to classify this as a 1 in the ensemble model based on the regression model. Okay, in other words, highest number wins. Then it also looks at the decision tree model. Says, oh, for this case, there's a 0.52 probability of attritting, 0.48 probability of no attritting. I'm going to call that one, since 5.2 is higher, we'll call that a 1, and I'm going to classify this as an attrit. And that's someone who left. It also goes back and looks at the neural network model. Neural network model says 0.3 probability of attrition, 0.7 probability of no attrition. That's much bigger. I'm going to classify it from that model as non-attriting. So we have 3 different results, don't we? Well, 2 different results, but 3 different models. 2 of them said this case was an attrition. 1 of them says it wasn't. What do I do with that? Well, I have to have some way of combining those results. And there are 4 ways in SAS Enterprise Miner to do that. First of all, there's the average method, okay? So we're averaging the posterior probabilities for a class variable and averaging the predicted values for an interval. So this was a class variable, either 1 or 0. So what do we have? Well, we have the probability of regression, we have the decision tree, and we have the neural net divided by 3. So for the 1, go back, the 1 we have 0.6, 0.52, and 0.3, don't we? We have 0.6, 0.52, and 0.3 divided by 3 gives us 0.473. What were the 3 probabilities for attrition? Or attrition, for not attriting, rather. 0.4, 0.48, and 0.7. So we combine those and divide by 3. Pretty simple process. And we get 0.527. Again, highest number wins. So the answer coming out of the ensemble node is no attrition if you're using this method. Okay. So that's the simplest method, probably the easiest, and pretty understandable. We're just taking those probabilities that came out of the models, and averaging them. The next method that you could use in SAS, Enterprise Minor, to combine those results is called the maximum methods. Probably can grasp this pretty quickly. The methods are combined by taking the maximum of the posterior probabilities for each model. You don't have to just have 3, by the way. You could have multiple. Okay, so what do I do for the maximum? Well, the maximum here is 0.6, the maximum here is 0.52, the maximum here is 0.7, right? Okay, so 0.6, 0.52, and 0.3 were the maximum of those 3 for attrition was 0.6, remember? So for attriting, 0.6, 0.52, 0.3. 0.6, 0.52, 0.3. What's the max of those 3? 0.6. Okay. How about for not attriting? Okay, again, go back real quick. For not attriting, 0.4, 0.48, and 0.7. What's the max of those 3? Well, it's 0.7. And again, 0.7 is bigger than 0.6, so the answer is no attrition. Now, let me add a little sidebar here. I'm going to send a email to Mr. Sarma because I think this is one of the few typos in his book. If you look in the book, I think it's page 40. Well, let me just find it real quick. 408. Under the maximum method, it looks like something got left out. Because it's clear that if you use the max for the attrition, the 1, it's 0.6, 0.52, 0.3, and the max of that is 0.6, just like I've shown right here. Below that, on page 408, it looks like he stopped and left out something. It says the probability of attrition 0 is 0.4, but then there's no 48 and no 70 listed. And so, clearly, if you put those 3 in, the 0.7 is the higher. And he says the answer is attrit equals 1 because there is a typo, I believe, 0.6 versus 0.4 because he left these out. If you put all 3 values in, which you should, then 0.7 is bigger than 0.6, and the answer is no attrition. So isn't that interesting? 2 of the models would have classified the case as an attrition, but these 2 methods, this one and this one, would classify the final one based on an ensemble approach as not attrited. Now, the next 2 are a little more complex, but not bad. There's a voting average method. Models are combined by averaging the posterior probabilities from the models which are in the majority group and only used for class targets. Of course, this was a class target. So who's in the majority group? Well, this said it was a 1, this said it was a 1, meaning attrit, this said it was a 0. So these 2 are in the majority group, right? Logistic regression and decision tree are in the majority group. I don't know what happens if you have an even number of models. I have to research that. So they're in the majority group. So logistic regression and decision tree are in the majority group, right? Because they both had a 1 and the other one had a 0. So they're in the majority. So we average the posterior probabilities from the models. So for attriting, we had 0.6 and 0.52, and we're only dividing by 2 now, not 3. And for not attriting, we have 0.4 and 0.48, dividing by 2. And of course, this is bigger than that. So we end up with an answer, attrition. You say, yep, this one attrited. So far, we've gotten 2 answers that said no attrition. We've gotten 1 answer that says attrition. Kind of interesting. Perplexing. You can see why it might be a little difficult to explain this. But again, depends on how you decide to average the results. The final one that's used in SAS Enterprise Minor is something called voting proportion method. Posterior probabilities are calculated as a ratio of the number of models in the majority group and the total number of models included. Ratio. Well, there were 2 models in the majority, okay, predicting 1. And there were 3 models total, 1, 2, 3. So the ratio is 2/3. So the probability of attriting is 2/3, 0.667. Probability of not attriting is 1/3, 0.333. 667, twice as much as 333. So the answer is, I pick attrition. So 4 methods with the same results, the same inputs, end up with different results. And I'll let you deal with that. Okay. I thought that was kind of interesting. We need to spend more time with that. I'm certainly going to spend more time with that because ensemble models are all the rage. I posted you, if you look at your guidance for the week and look at the supplementary links, there's a great video there on ensembles that's worth watching. Very little technical, but not bad, but very good. There's also some great links there explaining that this has become all the rage. Remember, there's no staticness about the world of analytics modeling, especially predictive modeling. Yes, we've had regression for a long time, and yes, we've had neural nets for a long time, and even decision trees for a relatively long time. But there's also new methods, support vector machines, and other things coming along. And this whole boosting and this whole random forest and the whole ensemble approach is relatively new. But if it gives you better answers, if it gives you more accurate answers, then of course that's why it's gaining some clout. And as I mentioned earlier in the course, SAS has a sort of a three-pronged effort they do. They consult a lot and help people build models or build them for them. They teach a lot to try to get the word out to help build more data scientists, and they do research. And part of their research is looking into building and developing and tweaking to come up with either better ways to converge models or better tweaks to models. So again, we continue to see new developments here, and I'll be talking more about some of the other new developments, which I find dazzling. Give you a little teaser for week 12. It's going to be, I think, impressed and blown away by something they got coming. Now, speaking of new models, let me remind you, before I forget, that on the 25th and 26th of July, SAS is going to be upgrading SAS Enterprise Miner to version 14.1. There is a website that I will point you to where you can see what's changing, but we might run into some hiccups during those times. If we do, we will make adjustments. I never make the students suffer for hiccups that are out of their control, and I'm not sure how difficult it will be, if any, to adjust to 14.1. There'll be some new features, some new things, maybe slightly different interface. Hopefully it'll run even faster and so forth. But just a reminder that that's going to happen. Okay, we don't control when SAS decides to upgrade the software. So right at the end of this course is not the optimum time, but that's when they're going to do it. So if you haven't yet seen that email I sent, that's going to happen. And I'll point you to a website where they're talking about the improvements. I think they're substantial. Okay. All right. So that's a little overview of ensembles. Two different kinds. One is sort of boosting things and getting things different. The other is sort of combining models that you're already aware of or the boosted ones. You might begin messing around and trying and experimenting with the ensemble. Pull that node in, take a look at some of the options, which are basically the ways to combine things, and see what you think. You might want to use that an ensemble approach for assignment 4. It's one of the options. Okay. When we get into week 11, which will be next week, we're going to talk about text mining. Now, you get a lot more on unstructured data and how to handle unstructured data when you get into Data640, your next course. But I thought it's interesting to give you a little heads up on one of the more exciting and interesting things coming. The ability to mine text, the ability to deal with unstructured data, such as pictures, videos, audio files, as well as text, is growing in importance. And then, of course, as always, if you have interesting insights, tidbits, hints, tips, questions, whatever, feel free to contribute those to the discussion area, as always, because this is kind of a new frontier, and I'm very excited about it, because I think it's going to be interesting to see how we do on this stuff. Okay, as always, my last slide. You've seen this before. You can ask a question now. I'll try to answer it if you feel like you need to do that. Otherwise, during the week, feel free. And please, I've seen a couple of people mention that they had trouble getting SAS to work in the last day or so, and that's fine. That sometimes happens. We've had that happen occasionally, not too often this semester, not as much as last semester. Maybe I don't know if they've started their upgrade sooner. I hope not. But I hope the upgrade will go smooth. And I'm going to point you to, again, a site where you can look at some of the new features and at least read about them. I think that'll be helpful. And as always, be sure to email me or phone me if you have a personal problem or something really disastrous happening, and I'll accommodate you. Okay, so that's where we stand. Interesting stuff. It's really interesting. The more you learn about the world of predictive analytics, the more you use SAS Enterprise Miner, I think the more interesting it becomes. As you grow accustomed to the interface and the options and learn about the techniques and understand what's going on, you really begin to feel sort of, aha, I see how this unfolds. And I think that's crucial. It's not like there isn't other good software out there. There is. And certainly we're going to make sure you have some experience with Hadoop and other software packages during this program. In fact, we're going to be adding a few more weeks of R into the Data610 course for the upcoming semesters, it looks like, I think. Getting started on that. So we're looking at various things, but the ensembles are one of the hottest techniques, as you'll see if you look at some of the links I've provided where they discuss that. All right, I don't see any questions coming, so I'm going to stop sharing. And the next thing I do is stop the recording and post the link to the recording as soon as I have it as